Okay. Next to the last chapter, number 17. So we're going to pick up where we left off in the first semester with thermochemistry. This chapter is a continuation of thermodynamics. We're going to focus in particular on concepts that describe spontaneous reactions. What constitutes a spontaneous reaction? How do we get a spontaneous reaction? There are lots of different principles that come from chemistry, but there are just a few major principles, or I should say driving forces for understanding how and why chemical reactions occur. And we've talked about a few of them in terms of how do you detect a chemical reaction? Sometimes you'll see a gas produced, you'll see a color change, see heat evolved. Those are clues. What we want is an understanding of why something happens. And there are many chemical reactions that can't be explained with those clues. They may accompany the reaction, but the explanation for the reaction depends more on the upcoming concepts. All right, so let's do just a little bit of review. You'll recall this particular diagram where we have the progress of the reaction on the x-axis and the energy of all the reactants and products and intermediates displayed in that curve. And we know that the way this curve is drawn, right, the energy level here is going to be higher than the products. So that means it's exothermic. Right? You have more energy here, you have less energy in the products. So where did the energy go? Well, from here to here is the enthalpy of the reaction, that the heat evolved. And we also know that in here, the activation energy is between here and here. So we have to put that much energy in to get the reaction to go. Well, we spent time in one chapter with chemical kinetics, and the kinetics are considered this region in here. Thermodynamics considers only this part of the reaction and this part of the reaction, in the beginning and the end. The domain of kinetics is a region that we're concerned with the path. What path does the reaction take? Now, one of the best ways to describe why path matters is if we introduced a catalyst. If we introduce a catalyst, then the activation energy becomes less, right? It becomes here. And that's because the reaction follows a different path with the catalyst than it does without the catalyst. Without the catalyst, it takes more energy, so the reaction runs slower. With a catalyst, the path is different, and the amount of energy required is less. But when we talk about the reactants and products only, and we're not concerned with the intermediate, we only care about where it started, where it ended. Now we're talking about a state function of this chemical reaction. We only care about the beginning states and the end states. Doesn't matter what happens in between. And that's where we're going to focus our attention with spontaneous processes, entropy, which I have to define for you in a second, and then free energy. Okay. The thermodynamics, being involved with these two, helps us to predict whether a reaction is spontaneous in the forward direction or spontaneous in the reverse. If it's spontaneous in the forward, it's non-spontaneous in the reverse. Spontaneous, by that we mean the process occurs without any outside intervention, right? You put the two or more reactants together, or just one reactant for that matter, and it will progress to the products. Now, that doesn't say anything about how fast it gets there. That's kinetics, that's in this part. But the spontaneity of the reaction, it will go without any outside intervention from here to here, or if it's reversed from there to there. So let's proceed to the next slide. So let's say we have 2.4 moles of gas contained in a 4-liter bulb at a constant temperature of 32 degrees. So let's draw a picture. 4-liter bulb. Okay. So that's a 4-liter bulb. And it's connected to another bulb with a valve. And the other bulb is 20 liters. Right? So it's huge. Right? And this is a vacuum. Where we have 2.4 moles of gas in this side, and the temperature is the same. Right? There's no difference in temperature between the two. Okay? What should happen when we open the valve? But intuitively, we know what's going to happen, right? The gas is going to and fill up that space, and the pressure between the two will equalize. Right? Well, what caused it to happen? Right? We can't explain it with chemistry. This is more of a physics problem, but there's a lot of overlap between chemistry and physics, and that's many of the advances that we're going to discuss today in thermodynamics occurred because of the activities of physicists and not chemists. But in those days, in the 19th and early 20th century, the lines were kind of blurred between physicists and chemists. Okay, so we know it's going to happen. We just can't explain it in chemical terms, even though we intuitively know what's going to happen. So what we need to do is define some terms so that we can start discussing this in a rational form. I think we've defined enthalpy before. Right? That's a measure of the heat potential of a reaction. Enthalpy. And when we went through the discussion of thermochemistry, we were concerned with measuring heat transfers. And so when we saw the temperature, we put two ingredients together in the lab, and we saw the temperature rise. We saw that as an exothermic reaction. And we measured the heat as Q. Now, these two are related, but they're not the same. Right? Q is simply heat flow measured by a temperature change. W is equal to work. And this is the scientific definition of work. If you've had physics, if you haven't had physics, then that's okay. I'm going to define it for you anyway. Work is defined as a force applied through a distance. And so if I push on this wall, I'm applying a force, but nothing's moving. So I'm not doing any work. Well, I'm expending energy, right? So where's the energy go? Well, the energy goes in here. I'm heating up my hand in the wall by pushing on it. Well, probably a little bit of the floor, but it's not useful work. It's not being transferred to something as a force through a distance. Okay. So now that we have a definition for Q and W, we can define internal energy. And this goes back to the way of thinking that I proposed, I think when we were talking about thermochemistry, is defining system and surroundings. Do you remember that? No, okay. This is our system, and it's anything we define as a system, and everything else is surroundings. Maybe that's coming up. I'm just checking my notes to see. Yeah, I think I have already defined it. That was in the chapter on thermochemistry, system and surroundings. Well, if we define our system and there's some type of barrier between the two, then the surroundings would be the rest of the universe. That's a little hard to get a handle on because the universe is a big place. So what we tend to do is we isolate. So here's the systems and here's the surroundings, and everything else we don't care about. Okay. We'll talk about that a little more. The internal energy, it references the system. Right? We're defining the internal energy in terms of a change in heat, right? Whatever the heat measured, change of heat movement between the two, right? It can go this way or it can go that way. Right? And the work done in terms of the system. Does the system do work on the surroundings? Or does the surroundings do work on the system? Okay, and everything is relative to the system. So if we need to put a positive or negative sign on the quantities that are expressed, it's reference to the system. So if the heat transfers from the surroundings to the system, it's positive value. If the system transfers heat to the surroundings, then it's a negative value. And the same thing for work, right? If work is done by the surroundings on the system, it's a positive value. And if the system does work on the surroundings, it's a negative value. Okay. All right. So if we add those values together, Q plus W, that's an expression of any change in internal energy for the system. Okay. I had to define those terms. Now we can go back to enthalpy. Now that we've defined internal energy, enthalpy is also equal to any change in internal energy plus, actually, that's true. If the pressure is constant, that's true. But if the pressure changes, then it's a change in the pressure times volume. P delta V is only true if the pressure does not change during the process. Okay, so those are our defined terms. And let's see. All right. Let's go back to this, our gas. I erased it, but I'm sure it's embedded in your mind. If we reconsider that 4-liter bulb with 2.4 moles of gas in it connected to a vacuum bulb with 20-liter capacity, and we open it, assume the temperature is constant, right, at 32 degrees. What's the delta H, delta E, Q, and W for the process you described above? Well, if you look at them in terms of their definitions, right? If the gas moves from one to the other, has there been any work done? Well, there's no work at all. So in that case, there'd be zero. Was there any heat transfer? Temperature is constant, and that's how we measure heat transfer, right? So the temperature is constant. That means no heat flow either. That means there was no change in internal energy. Okay. And if this is zero, That would be zero. How about pressure times volume? Well, when we open the valve, of course, the pressure is going to go down, but the volume is going to go up. And there was actually no change in this value of pressure times volume because of Boyle's law, right? It's a constant. And so pressure times volume is a constant. And if we change the volume, the pressure is going to respond in the opposite direction. So there was really no change in pressure volume either. That means all of these values are zero for that process. Okay, that leaves us with a problem. How do we explain what happened? Okay. All are equal to zero. So we've got to come up with an explanation for why that gas moved. Right? What was making it go from the 4-liter bulb into the 20-liter bulb until the pressure is equalized. Right? So, well, here's an explanation for the constant temperature process means that, well, if the pressure is constant, the temperature is constant, the heat flow is going to be zero and delta H is going to be zero too. I approached it from this angle, but if you approach it from the temperature side, it's also equal to zero for that reason, because no temperature change was involved. Right? And there was, the gas was not moving against a pressure of any kind. It was being swept into an evacuated bulb. There was no work done whatsoever. Right, so there we have internal energy was also zero. Okay, what's the driving force for the process? We need a new explanation. That's it. I better leave that there for now. We need a new explanation, and we have to come up with a new idea. It's called entropy. You may have heard of entropy from time to time in the popular literature. But from a scientific standpoint, it was proposed by Rudolf Clausius in 1865. Yeah, I think I got a picture of it. Seems like everybody during the mid-1800s, when they had their portraits made, they all looked like that. Look at kind of a scowl on their faces. So this is what we were describing earlier. When you open the valve, and these are individual molecules of gas. That's the red dots that we're trying to explain. Notice anything different between the two? In the first situation, they seem to be closer together, right? And in the bottom situation, they're further apart. Right? The number of molecules, the same number of molecules now are able to occupy a larger space. That's the main difference. And in so doing, they have increased their entropy. Now, for convenience, entropy is often defined as a measure of randomness. The more random, the higher the entropy. And higher entropy is considered a driving force for reactions. Or for physical processes, for that matter, either one. So what we have witnessed here is an increase in entropy. Now, from a scientific standpoint, the description of entropy needs to be a little more refined, but as a rationalizing process, you can think of entropy as a measure of disorder. So more disordered. So if you have a teenage son, you go walk into his bedroom, you'll see very high entropy, right? Dirty clothes everywhere. Whatever he was doing last is left hanging. Increased entropy. If you go into your daughter's room, this varies, of course, but generally speaking, you may expect to find a more ordered arrangement of things and no dirty clothes laying around. So The driving force then for every spontaneous reaction is an increase in entropy. Every spontaneous reaction can be traced to an increase in entropy. Now, this could be, the authors of the textbook refer to this as entropy of the universe. I prefer to think of it as entropy of the system versus entropy of the surroundings. It could be entropy here versus entropy there. And I think it's easier to get a handle on it if we restrict our system surroundings to a certain part of the universe. But as a matter of fact, the entropy of the universe, the change in entropy of the universe is always positive. The entropy, you've heard it, maybe you've heard it said, the entropy is, the universe is running down. Right? That just means that the energy available in the universe is, but you're less able to extract useful work from it as the universe ages. And that also goes back to the concept of the expanding universe. Right? Edwin Hubble proved that one back in the late 19th century, early 20th century, when he measured the expansion of the universe in terms of the redshift of light coming from distant galaxies. He proved that the universe is in fact expanding in all directions around us. So the universe is increasing in entropy always. There are local pockets of concentrated energy and order that we can use to drive other processes. So let's get back to the slide here. So if this term S equaling entropy is always measured as a change in entropy. In fact, entropy itself cannot be measured directly, not like temperature, not like heat flow, things like that. Entropy has to be calculated. And if the value is greater than 0, we say that the entropy is increasing. If it's less than 0, entropy is decreasing. Now, this concept of disorder is an oversimplification, but it's often useful as an introduction to the concept. In fact, entropy measures the number of possible arrangements. It's a statistical process. What are the total number of possible arrangements of all the particles in a system? Right? If you have a large number of possible arrangements, then you have high entropy. If you have a very small number of possible arrangements, you have low entropy. So with that being said, if you take a liquid, say just a glass of water, it has a certain entropy. And if you boil it, then it expands into a larger space. It has more possible arrangements, more possible, what we call microstates. The more microstates you have, the higher the entropy. So if you change liquid into a gas, that means it has more microstates available to it, and that's a higher entropy. If you freeze water and fix its molecules into a crystal matrix, then it has fewer microstates available to it, and the entropy decreases. Okay, let's look at it in terms of these two bulbs, and we have 4 molecules in each one, labeled A, B, C, and D. All right, how many possible microstates does the first one have, where all of the molecules are on one side? It's only one possibility. They're all on one side. And if you go to the bottom, then you'll find that if you go down here to the bottom, if they all move to the other side, there's only one possible microstate for those. But if you say, what if we put 1 on the right and leave 3 on the left? Well, you have 4 possibilities, right? It could be A on the right, or B on the right, or C on the right, or D on the right. So you have 4 possibilities. More microstates possible there. If we put 2 on the right and leave 2 on the left, then you have an increased number of microstates, a total of 6 possible. Right? If you put 3 on the right and leave 1 on the left, then you have another 4 microstates possible. So which one is the most probable is the one in the middle. There are more possible microstates when you have equally distributed 2 on the right, 2 on the left. Okay. That's the wrong button. There we go. So that's the microstate definition. Any configuration that gives a unique arrangement of particles. Let's see, what is that in terms of mathematics? That's a permutation, isn't it? I think that's a permutation. All right. So with the description I just gave you about solids, liquids, and gases, we would expect to see that the entropy, and they're not using a delta there because we're saying we're trying to keep things simple. Right? When you actually do calculations, you're looking for a change in entropy. But if you think of entropy in terms of what would it be from absolute 0 to here, then yeah, you could say that's an absolute value. So the value of entropy for the solid would be less than the entropy for the liquid, which would be much, much less than the entropy for the gas. And you can think of that in terms of disorder. Hopefully, over time, you'll get comfortable with the concept of microstates, because that's where the reality lies. Oh, this is not covered in the textbook. So I better pay close attention to this. There are, you can subdivide entropy into 2 types of entropy. One has to do with energy. Right? If you think of temperature as a measure of the average kinetic energy of all the particles in a substance. Kinetic energy can either be like a gas, where you have gas molecules just zipping around like that, banging into each other. That's easy to think of. They have kinetic energy. But if you condense it into a liquid, then they're not as free to move. They can move past one another, but they don't have the freedom. And we've decreased the energy of the liquid. We've extracted energy from the gas to condense it into a liquid. Well, going further, you extract more energy from that liquid and make a solid. And what you're doing is you're changing the number of microstates by extracting energy from the system. So we can view that in terms of energy entropy. So an exothermic process implies that there's an increase in energy randomness for the surroundings. Exothermic, right here. You're increasing the energy of the surroundings, which means you're increasing here would be positive. You're increasing the entropy of the surroundings, while at the same time decreasing the entropy of the system. Okay. An endothermic process goes the other direction. Right? So this would be, you would decrease the entropy of the surroundings and increase the entropy of the system by an endothermic process. And that can be viewed as a change in energy entropy. Now, I said there were two ways that we could view entropy. One is energy entropy, and the other, let's see, hopefully I have that slide. Okay. I must have missed it. Okay. The other type of entropy, we have energy entropy and we have positional entropy. And the positional entropy is more like the one that we described with those bulbs and the four molecules that can move. Where are they? That determines their entropy. But you can have a change in entropy in a solid simply by heating it up. And you don't have to change the state. You just change the energy of all the molecules inside the solid, and you're changing its entropy, its energy entropy. All right. So let's look at this in practical terms. See if we're sort of developing an intuition for entropy. Let's see if we can predict the sign of a change in entropy for each of the following. Increasing entropy, of course, is going to be positive. Okay, evaporation of alcohol. If the alcohol, say you put alcohol on your skin and it gets cool, and it evaporates as it absorbs heat from your hand. It evaporates. So what's the change in entropy for the alcohol? Should be positive, right? It increases the number of, I'll come back to that in a minute, increases the number of microstates possible, going from a liquid to a gas. That little inset up there was proposed by Boltzmann, and this entropy equals K natural log W. W is his expression, his mathematical expression for the number of possible microstates in the system, right? That's a useful mathematical expression, but for mathematicians and theoretical physicists, but it's not very useful for chemists. So that's just to explain that it's theoretical, right? It's a calculated value. And we're going to calculate some later using a little more useful forms of the equations. Okay, freezing of water. Water goes from a liquid to a solid. Right, should decrease. Compress an ideal gas at constant temperature. Right, you're compressing it. Right, the entropy should decrease. Right, you're giving it fewer microstates available. You're decreasing its volume for the same amount of gas. It doesn't have as many possible microstates. You heat an ideal gas at constant pressure. Increase. Yep, you're increasing its energy entropy. And dissolve sodium chloride in water. You sort of have to think about the sodium chloride as your focus, as your system. It's going from a solid to a dissolved ionic compound. Increase. Yes. That would increase its entropy. Yep. Okay. This that we've been talking about is, in fact, the second law of thermodynamics. And in words, it says that any spontaneous process, one that requires no intervention, there is always an increase in entropy of the universe. Okay. And I put this note in here because of the way your authors think of universe. Sometimes they mean universe is the universe, and sometimes the universe is just our isolated system surroundings. So I try to differentiate between those two whenever possible. There we go. But this is true. The entropy change for the universe, and this by this I mean the entire universe, is always greater than zero. It's always increasing. You know, like I said before, there can be local pockets of decreasing entropy versus increasing entropy, and particularly when you couple systems together or systems and surroundings, you can find that one increases entropy and the other one decreases. That's entirely possible, and in fact, we see on a local scale, we see decreasing, excuse me, increasing order or decreasing entropy in certain chemical processes. In the formation of a micelle. You know what a micelle is? No, you've never heard of that? The easiest way to describe a micelle is to think of a detergent molecule, or a soap molecule would be better. You know how soap is made? Take fat and add lye to it. Right? You have grandparents that used to make soap. Some people still make it. Well, you take that fat and you, it's called saponify. You saponify the fat with lye, and you get a molecule that's got an ionic end to it with, let's see, let's make this the negative end of the molecule. And then you have this long tail carbon chain. This is the go right out of my head. This is the ionic or polar end. This is the non-polar end. So when you put soap on your clothes or soap on your hands, most of the problems with getting clothes clean and the hands clean is oils, right? Non-polar compounds. So this part dissolves in the fat or the oil that's on your skin or in your clothes. And this part bridges the gap between there and water, because water is polar. Right? So that way you can wash it away. Well, when it does that, it forms a micelle. In other words, you've got a drop of oil here, and you've got these molecules like that with their polar ends. And they associate with water like that. And it forms this ordered structure. That's the micelle. That order would be a decrease in entropy, but it happens naturally. So the point is that even though the universe itself is always increasing in entropy, there are local pockets of order that form. Okay. So that was the second law of thermodynamics. The first law simply says that the total energy of the universe is the change in energy for the universe is zero. In other words, the universe has all the energy it had at the beginning, still has it now. And it's never going to change. First and second laws of thermodynamics. Now, when we look at our localized version, where we have a system and the surroundings, then we can say that the overall change here in entropy, I'm going to call this total entropy for this arrangement, is equal to the change in entropy for the system plus the change in entropy for the surroundings. Okay? All right. Yeah, that's the one I wrote. This is change in entropy total is equal to that. It's a more useful expression rather than saying universe. I think the authors get confused students when they say universe, and then they kind of flip back and forth between the whole universe and our isolated system surroundings. Okay, so the process, physical or chemical, will be spontaneous if this value is positive. Okay, so that means we have to say, what is the relative magnitude of each one of these? Right, if we have an entropy change here, it's a decreasing entropy here and increasing here. Well, what does that mean for the total? Right, when you add them together, they'll probably have opposite signs. So it depends. If the change for the system is positive, right, it's increasing entropy, and the surroundings are decreasing entropy, then if the change in entropy for the system is greater than the change in entropy for the surroundings, you'll have a spontaneous process. Okay. Now, if this total is zero, then we have something we've already studied called equilibrium. In that case, there's nothing happening. There's nothing apparently happening. Right? But we know from experience and from studying that an equilibrium has processes that are going backwards and forwards. The reaction is proceeding forward and backward at the same rate. But there's no change in entropy as a consequence of those processes. Okay. So if we look at this one where we have something, whatever, is liquid, and it's going to solid or solid going to liquid, which direction involves an increase in the energy randomness? Well, let's see. In order to go, I'm sorry?
Solid and liquid?
Yeah, you would expect an increase in energy entropy. Oops, wrong side. From this side. Energy. This one should be an increase in the energy entropy. That would be. How about positional entropy?
Liquid and solid?
An increase. It should be the same both directions, shouldn't it?
I just saw positional randomness.
Yeah, positional randomness. You're going from solid to liquid. The liquid gives you more possible microstates. It's not locked into it.
More stationary.
That would be a decrease in entropy, wouldn't it?
Yeah, that's what I was thinking.
Yes. So both of them should go to the left. Okay. Liquid to solid would be exothermic. Okay. If it's exothermic, if delta H is going that direction, would be exothermic, would be negative. That means heat would flow out like that. Would flow out of the system. Energy randomness favors formation of the solid, decreasing from liquid to solid. Well, in that case, it's a little hard to follow because we haven't spoken about what's happening to the surroundings. If the surroundings are increasing in entropy faster or at a larger amount than the system, then yeah, this would be favored going from liquid to solid. Whereas positional entropy would reduce the number of microstates to the right and would be less favored. So the balance between the two types is what you're interested in. And we can't know that unless we know the absolute values for each one. Okay. If you get confused from time to time, it's normal. If you grab on and understand it, that's great. Okay, as temperature increases or decreases, which takes precedence? As temperature increases, positional randomness dominates. As temperature increases, positional randomness dominates. So if we have heat going the other direction, so that we get an influx of energy and increased energy entropy, the positional randomness.
Would that,
Okay, I see where this is going. Yeah, go ahead.
would that be similar to, where the heating an ideal gas at constant pressure?
The focus here is on temperature matters. Which one is dominant? Is energy entropy dominant or positional entropy dominant as temperature changes? If we have a constant temperature that is high temperature, let's say our system is at high temperature. All right, it's already got a whopping amount of energy entropy. So adding energy to it is not going to affect it that much. It's like if I were a millionaire, which I'm not, but if I were, and you gave me $10, it wouldn't matter. Okay? But if I am at low temperature, if I'm like I am now, kind of a poor teacher, and you gave me 10 or 20 bucks, that'd be a big deal relative to my current situation. So what we're saying is, at higher temperature, positional randomness is more important. Right? The arrangements possible is more important. Like a gas that's at high temperature, the positional entropy would be of more importance, say, if we expand the gas or we decrease its volume. That's more important, the positional effect. But at low temperature, the energy entropy is to be considered more influential at low temperature, because at low temperature, any change in temperature relative to its current position is a big deal. That's where this slide is going. Let's see which slide I'm on here. Decrease. Yeah, okay. So as temperature increases, the positional randomness dominates. So we go up in temperature, then the positional randomness is more important. And a release of energy becomes less important. If you release energy from your system, it's no big deal. Right? If I were a millionaire and I gave you $10, that wouldn't impact my bottom line much. And by the same token, if we decrease the temperature, now change in energy randomness is more important. So with that thought in mind, at what temperature is there a balance between energy and energy randomness and positional randomness, or energy entropy and positional entropy? at equilibrium. There's a balance between the two. And that equilibrium position for phase changes is at a melting point. For our liquid solids, it's at the melting point. That's where there's a balance between the two. Or if we were talking about a phase change from liquid to gas, it would be the boiling point. And we've also observed that at those particular places, phase changes, the temperature doesn't change. Right? As long as you've got, say, ice and water together, the temperature will always be 0 degrees, no matter how much energy you put into it. And same thing for water vapor and liquid water together. Temperature is going to be stable until you get only one phase. So at those positions, there's a balance between the positional and energy entropies. Okay. So let's see if we can expand our use of energy and positional randomness to encompass other types of processes and try to describe these as spontaneous, non-spontaneous, or maybe we can't tell. Okay, so let me erase this, that, and keep that. So if the process is exothermic and it becomes more positionally random, would we expect that to be spontaneous or non-spontaneous, or we can't tell? Exothermic, positionally random. Well, it depends on the temperature, I think. All right. The answer is supposed to be spontaneous. Let's see if I can make sense of that. If it's exothermic, the system is decreasing its energy randomness, and the surroundings are increasing their energy randomness. So that should be down here in this region, low temperature. That would be more desirable. But if we're also saying that the positional randomness increases, that is in an expanding gas, we're increasing this one. So we're increasing both of them, right? Both of them are increasing, so the temperature doesn't matter. We would expect that to be spontaneous no matter what the temperature is. Does that make any sense? Does that make sense? Right? If both are positive, if you're saying that positional randomness and energy randomness are increasing, then we would expect it to be spontaneous. In this case, we can't tell because we don't know at what temperature it's occurring. Right? Less positional random or exothermic. If it's endothermic and more positionally random, then we can't tell that one either because we don't know what temperature it's occurring. Now, if it's endothermic and less positionally random, we should expect that to be non-spontaneous. I think that this will become more useful if we can move beyond this theoretical entropy discussion and get down to doing actual calculations. All right. Well, that's A and D are not affected by temperature. B and C are affected depending on what temperature it is. All right. So how about the entropy of the surroundings? Now we're going to focus on that arrangement and home in on just the surroundings. we got the system, and we got the surroundings. Now we're going to try to say something about the surroundings in terms of the sign of delta S. It depends on the direction of the heat flow. Right? If heat is flowing into the surroundings, entropy should increase. So as heat leaves the system, the randomness in the surroundings increases. And in other words, if we are sending heat and we say delta H there, it actually should be Q. So if we're losing Q from the system, it's entering the surroundings, and the energy entropy of the surroundings is increasing. And so the surroundings are going to be increasing for an exothermic process. If the heat goes the other direction, then the surroundings, the entropy of the surroundings should be decreasing. And the change here depends on the temperature. Like we were saying before, the temperature influences at when does the temperature if we have high temperature, let's put this back up here again, low temperature, right? Which one dominates at high temperature? That's positional, right? Because the change in temperature doesn't matter that much. And at low temperature, we have energy entropy dominant. Okay, so temperature does matter. That's the point of this slide. Temperature does matter in calculating the entropy of the surroundings. So in other words, the delta S for the surroundings is directly proportional to the heat transferred, right? It's going to increase if we put like that. It's directly proportional to the heat transferred, but as the temperature increases, it becomes less important. So it's inversely proportional to the temperature. Right? So we put that in the denominator. 1 over T would be inversely proportional to temperature. All right, the expression then would be here. Well, the previous two slides, this delta S then would be equal to a change in heat divided by a change in temperature. The problem with this one is kind of like we've seen before. The convention here. If we measure a heat flow from the system, it's a negative value, but it's adding heat to the surroundings. Right? So it needs to be positive. So if this value is Q, we always measure Q and delta H with respect to the system. So if we're talking about the surroundings, we've got to change the sign in order to make this one positive. So that's why we put a negative here. The temperature doesn't matter. I mean, well, the temperature matters in absolute magnitude, but the temperature is what? Kelvin. Right? So it doesn't have a sign. Well, it's always positive. So one negative here will change that Q from a negative to a positive because Q is leaving a system. Now we change it to a positive. That says that the system entropy is increasing. Okay, see where that's required. Right, so that's why, and actually we're going to say it's delta H over T. So the enthalpy divided by T with a negative sign is equal to delta S surroundings. Now I think I've got a slide on this. The Q and the delta H, or maybe that was in, what was it, chapter 6? Maybe that's when we talked about it. Hold on a second. Yes, we did cover that in thermochemistry. When is Q equal to delta H? They're equal to each other only if the process is conducted at constant pressure. If the process is at constant pressure, then measured Q is equal to delta H. Okay. All right. Oh, here it is. How did I miss that? Well, that's good. Delta H, enthalpy, and Q are completely different values. Yes, that's true, because Q is measured and enthalpy is a thermodynamic potential related to internal energy. We said before that delta H is equal to a change in internal energy plus any change in pressure times volume. So that only works for gases. Okay. So if we take the equivalent of delta E, which is Q plus W, right? So Q plus W, we substitute that one. Q plus W is delta E. We substitute that one in here for that delta E. And then we solve. If at constant pressure, then we can pull the pressure outside the delta sign because it's not changing. It's a value, but it doesn't change. So if we pull the P outside, we get Q plus W plus P times delta V. We also know that and this description was in the thermochemistry description, we also know that work in a gas is equal to negative P delta V. The pressure is constant and the volume is changing, then work is measured as a negative pressure times volume. Well, if we substitute that one in there also for a PV, which is, oops, where's my arrow? Lost it. There it is. So now we're going to substitute W for this one minus PV. Right here. Right there, those two terms cancel out. Now delta H is equal to Q. So that's why enthalpy, or the thermodynamic potential for the reaction, is equal to a measured change in heat, Q, only when pressure is constant. So that's why most experiments, if possible, if at all possible, are conducted at constant pressure. So that way, any measured value of Q can be immediately equated to enthalpy. Oops. There we go. All right. How are we doing on time? I'm going to run out, of course. So if you have to leave, we've still got a lot of ground to cover. So I'm gonna finish this by hook or by crook. So remember the previous expression for the total entropy. It's equal to the change in entropy for the system plus the change in entropy for the surroundings. Right? Okay, so let's see. All right. Let me put it in the same order they do. That was right. System, delta S for the system, plus delta S for the surroundings. equals delta S total. They call it universe, I call it total. Okay. If the entropy of the system is increasing and the entropy of the surroundings are both increasing, right, then it's a no-brainer. Delta S total is positive, and that process in the forward direction is spontaneous. Okay. If, on the other hand, the entropy for the system and the entropy for the surroundings are both decreasing, that's a no-brainer too. It's non-spontaneous in the forward direction, but spontaneous in the reverse direction. Okay. What if we have this situation? Entropy of the system is increasing, entropy of the surroundings is decreasing, right? This is only positive if system is greater than surroundings. Okay. So you can't tell until you know the absolute value. And conversely, if the entropy of the surroundings is increasing, the entropy of the system is decreasing, then that also requires knowledge of the absolute values. Okay. Now, now we're going to get to some useful. Well, we do have one. We do have one equation that we've got that's fairly useful, right? The surroundings is equal to negative delta H over T. We've got that. Now we've got this brilliant chemist, physical chemist, Josiah Gibbs, who did his work at the late 19th century. He was interested in chemical reactions, how much of that enthalpy, how much of that is available for useful work. Right. So he worked on that for a while, and he wasn't the only one working on it. And what he came up with was an expression of the free energy, and we give it a delta G in honor of Gibbs. There are other versions that other people are working on, but this one's the most commonly used. So we're going to focus on that one. So the free energy is the amount of energy change in a reaction that is available to do useful work, that force times distance. Well, we've got the enthalpy, right? We know how much that is, but we have to steal some of that away. In every process, you lose that much, right? So this amount, you have to subtract that much to find out how much is available for useful work. Okay. So if we do a little mathematical gyration here and divide the whole thing through by a negative T, right? Okay, so that cancels this T, that negative T. It leaves us with negative delta G over T equals delta H over negative T. Well, you see here, this one is delta S surroundings. There. And if we substitute those values in, delta S for surroundings, and this delta S is always for the system. We didn't write it in there, but that's what it is. And this is the system, delta S for the system. Then negative delta G over T is equal to delta S total. So now we have another equation. The total entropy of the system, change entropy, is negative delta G over T. All right. Well, we know that if this is positive, we have a spontaneous reaction, correct? So what does that mean? that means that delta G is negative. A negative times a negative is positive. If delta G is negative, then we have a spontaneous reaction. Oh. Oops, went too far. There we go. Okay. All right. So what are we trying to do here? A liquid is vaporized at its boiling point, constant pressure. Predict the signs of these. If it's vaporized, is it doing any work? No, I mean, if you just have a pot of water on the stove and you're boiling it, it's not pushing against any pressure. It's not applying any force. There's no work being done. Well, they just made a liar out of me. A liquid is vaporized at its boiling point. Predict the signs. All right, that's only valid if the vaporizing liquid is pushing against something. Let's say it's pushing against the lid, right? And you know it's boiling when the lid starts to rattle. Okay. So heat is being added. That means it's positive. Well, that's true. We're adding heat to the system. So what's delta H? Well, since the pressure is constant, then delta H is the same as Q. Right, so it's also positive. What about delta S for the system? Well, let's see. The system is going from liquid to gas. It's increasing energy entropy. Right? It's more disordered. The gas is more disordered than liquid, so yeah, it's going positive. How about the delta S for the surroundings? The surroundings have to become more ordered as we add heat to the system. So the surroundings are going to be negative. How about delta G? At the boiling point, the system is at equilibrium. So delta G is equal to 0. That means delta S total is the delta S system plus delta S surroundings. They would have to be equal in magnitude. Those two, delta S system, delta S surroundings, they're equal in magnitude. Add them together, you get 0. Right? So that means no matter what the temperature is, delta G has to be 0. And that's true for any equilibrium. Delta G is 0 at equilibrium. Okay, so in that case, yes, if delta G is equal to 0, then that's equal to delta S, and this is system, remember, system, minus, excuse me, H, sorry, delta S system, okay? So if this is 0, then that's equal to delta H minus T delta S system, and delta H is equal to, just bring this one over here and make it a positive, T delta S system. Okay. So at equilibrium, delta H is equal to T times delta S for the system. That's another one. Delta H equals T delta S for the system. By the way, at equilibrium, the delta S for the system has to be equal in magnitude and opposite in sign. Right? If it's at equilibrium and delta S is 0, total is 0, then this one would have to just be delta H over T. And that's true only at equilibrium. Right? You just change the sign, you got that. Okay. I got 5 minutes and probably a bunch of slides to go, don't I? Yeah, well, like I said, if you have to go, I'll just keep going and recording. Okay, let's say the value of enthalpy of vaporization of a substance X is 45.7 kilojoules per mole. Let's just write that up there. Delta H vaporization equals 45.7 kilojoules per mole. Go. And its normal boiling point is 72.5 degrees. So its boiling point is 72.5 degrees C. So we're probably going to have to add 273 to that also to find out the K. What's delta S system, delta S surroundings, and delta G for the vaporization of 1 mole of this substance at 72.5 and 1 atmosphere pressure? Well, if we're at the boiling point, right, delta G is 0, right? Should be. Yeah, delta G is 0. And the delta S for surroundings is equal to negative 45.7 kilojoules per mole divided by temperature, which is 345.5. Okay. Now notice the answer here is in joules. So you'd have to change this to joules, right? Remember how we do that? Kilo means times 10 to the third, not plus, times 10 to the third joules. Then we divide that out, and that gives us a negative 132 joules per K mole. Those are the units of delta S, joules per K mole. And enthalpies, entropies typically are reported in joules. And enthalpies are typically reported in kilojoules. So always be aware of that fact. When you start to do these calculations, you've got to change the values. I typically change to joules. And then if I need to change back, I can do that. Okay, so the delta S for surroundings is negative 132 joules per K mole. At equilibrium, the value of system has to be equal to, but opposite in sign for this one. So delta S system, there would be a positive 132 joules per K mole. Okay. Oh, Professor Day is going to talk. All right. Let me see. How long is he going to take? 8 minutes.
Professor Dave here. Let's learn the laws of thermodynamics.
He knows a lot about the science stuff. Professor Dave explains.
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random. That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around, entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own. Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T, so entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand, because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap. You need soap to wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the nonpolar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water-soluble due to the polar heads facing out. That's how soap works, and that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy-storing processes. In this way, systems can defy entropy on the small scale, but the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
While Professor Dave was talking, I put these problems up on the board. Since we've only got between Tuesday and Thursday, before we're going to need a review, so we'll be ready for an exam on next Tuesday. These are the problems I'm going to use in the review documents on Thursday. So it's being recorded. So if you're limited on time, focus your energies on these for version 1 and version 2 for those numbers, and those are the ones we'll cover. And of course, you're free to look at any of the others. All right, so Professor Dave described the influence of using Gibbs free energy equation. The sign of enthalpy and entropy can be, you can have, if you have a negative enthalpy and a positive entropy, you will always be negative delta G. Doesn't matter what the temperature is. So if you have a negative here and positive there, this will always be negative. And if you have a positive here and a negative there, it will always be positive, which means it's non-spontaneous. This is spontaneous. This is non-spontaneous in the forward direction at any temperature. Okay. When we go to a mix of, say we have 2 negatives, right? So that would make this one negative, which is good, but it make this one positive. So we need to minimize this one. If we want this one to be small or positive, we need low temperature. A small value here would keep this one, this positive overall, negative, negative, positive overall small enough so that the reaction is still negative, Gibbs free energy. And if we went the other direction, if we have both positives, then this one would have to be high temperature. because this is a positive, but it's got a negative value, and this one's a positive, then the high temperature would mean that this term would be sufficiently negative to make this one negative and spontaneous at high temperature. Okay, so at low temperature, this would be negative, and at high temperature, this arrangement would be negative. Okay, that's what that chart says. Okay, let's see what we can glean from this slide. Yeah, we already lost one. Gas A reacts with gas B to form gas AB. All right, so this is a diatomic A gas plus the diatomic B gas reacts with each other to make an AB gas. Right? So that would be two of these to balance it. The bond energy of AB is much greater than that of either reactant. So what have we done? If the bond energy here is greater than it is for either of these, we have an endothermic process. Right? The endothermic, we've actually added energy. If the bond energy here is greater than it is for either of these two together, then we've added. So what would be the signs for, let's see, we're looking at delta H, delta S surroundings, delta S system, and delta S total. We want to know the signs there. Well, if this is energy going in, this is endothermic, right? Oh, beware, I better look at that. This problem says that AB bond is stronger than A or B, AA or BB. That means more energy is required to break AB than either A or B. More energy must be supplied to break AB bond in its lower energy state than either A or B. With that in mind. Next slide. Oh, okay. You remember that equation? I take the bond energies, add the bond energies together for reactants and products, minus we add the energy required to break the bonds and subtract the energy required that is given off by forming bonds. Okay. So it says this is exothermic. Okay, I misread it. The bond energy here, it takes more energy to break that bond than it does to break these bonds. Okay, that's why I put that caution in there. If we have to put more energy in to break this bond, that means this is more stable. It's at a lower energy. Okay. Did I confuse anybody? I started to confuse myself. Probably why I put that beware in there. It takes more energy to break this bond. It's more stable than either of these. So this is at a lower energy. That means it's exothermic. Okay. Delta S surroundings, we take a negative delta H over T, which means this should be positive, correct? If that's a negative and this is a negative, that should be positive. Okay. How about the system? Well, we don't know. We don't know for sure. We're going to say that the delta S for the system is roughly no change. And what we're going to look at positional entropy here. you got 1 mole there, 1 mole there, and 2 moles here. So you got equal number of moles of gases on either side. So we're saying that positionally, the entropy hasn't changed. So we're going to assume with that line of reasoning that delta S system is 0. And that means the total would have to be positive. This is the only kicker right here. Assuming that this is 0 because you have 1, 2, and 2 on both sides. You have the same number on either side. Okay. Professor Dave also mentioned the third law of thermodynamics, and this is only important to people who spend their lives doing this stuff on a day-to-day basis. But it does tell us something about the entropy that we see at our temperature. Right, we're way above absolute 0. At absolute 0, the entropy is assumed to be 0 for a perfect crystal. At 0 K, entropy is 0. So in that respect, entropy and Kelvin are a lot alike because they're always positive values. 0. They're always positive values for individual systems or surroundings. If they're measured against absolute 0, the perfect crystal, then they're positive. So what that means is if you look up the values for in a reference manual for entropies of various compounds or elements for that matter, their values are always going to be positive because they're measured against absolute 0, which is 0. Okay, and the only way that you can get positives or negatives is the way they're used in these formulas. Okay, so the same way that we can get delta H, right, by summing the delta H's of the products minus the sum of the delta H's for the reactants. You can do the same thing with, and this is under standard conditions, right? That's what that 0. Right? So if we do that under standard conditions, that means you can read it from a reference manual. Then we take, be better than that, the summation of the entropies. And this means that they're measured against absolute 0. So when you look at them in a chart, there's going to be a value here. And then you have so many of them. This is for products. And this subtract the entropies for the reactants. So we can calculate the standard entropies of a reaction if we know the values for the reactants and the products. This is just a general statement. Overall, this value tends to increase as the complexity of the molecule increases. Water versus diatomic hydrogen is a good example. Water is a bit more complicated than diatomic hydrogen, and we see that its entropy is based upon these various types of movements. We have these synchronous stretches here in these bonds. Right? Here we have a bending. Here we have an asynchronous stretching, and here we have rotation. Those are the things that water can undergo, whether it's gas, liquid, or solid. These will all be happening. But for hydrogen, diatomic hydrogen can only stretch and rotate. So it would, you have 2 hydrogen molecules and they could either do this or they could like that. That's it. So their entropy value for diatomic hydrogen should be a lower value, lesser value than for water. Okay. So if we have this reaction where we react sodium and water to make sodium hydroxide and hydrogen gas, which is very exothermic. In fact, actually it doesn't work as well with sodium as it does with potassium. If you put potassium in water, you get more heat. And as the hydrogen bubbles to the surface, there's enough heat that when it mixes with air, the heat will ignite it. Right? So you can get flames on the surface of the water if you drop potassium in there. Sodium just gets really, really hot. Anyway, if we want to know the entropy for this reaction, the total reaction, we need sodium hydroxide, which is 50 times 2, plus hydrogen, which is 131 times 1, add those together, and then subtract sodium, 51 times 2, plus 2 times water at 70. And you get the change in entropy under standard conditions. Right? That's what that little 0 is for. Under standard conditions, you get the change in entropy for that reaction. Okay. And you put all those together, and you get a change in entropy of only 11 joules per K. You can do the same thing with Gibbs free energy. Right? You look up these values. Gibbs free energy. And calculate the Gibbs free energy for any given reaction under standard conditions. Whereas these values, even for elements, you will always have a value here. But for elements, remember, enthalpies, the elements are 0 enthalpies. Same thing for Gibbs. Under standard conditions, the elements under their most stable room temperature and pressure conditions are 0. Okay. Stable diatomic molecule spontaneously forms from its atoms. Diatomic molecule spontaneously forms from its atoms. So there's your generic. What's the sign of delta G? Let's go backwards. What would be delta G for this one? The sign would be negative. The key there is spontaneous. Spontaneously forms means that delta G has to be negative. How about delta S? Well, we can look at this in terms of positional entropy. It spontaneously forms from here to here. From these two to that one, you're going from 2 to 1. So this one should also be negative. Right? Less ordered. More ordered from 2 independents to 1. And then how about, let's see, we have those coming up. Oh, well. If you're going from these and you're forming a bond, that usually means delta H is exothermic. Because it takes energy to break that bond. It's more stable than these separate. So you would have to add energy to that to break the bond, and that means energy is on this side, which means exothermic. Okay. Now, let's see. Am I getting close? Yeah, we're getting there. All right. So let's see. We've got a sample problem here. This should be useful for the review questions. So if we have this system at 25 degrees C, let's just go ahead and add 273 to it. And we're taking PCl3 gas. Oops, got chlorine. plus chlorine gas forms PCl5 gas. There we go. And delta G for this one is, under standard conditions, is minus 92.5 kilojoules. And this is standard temperature, 25 degrees. All right. What will happen to the ratio of partial pressures of PCl5? Partial pressure of PCl5 to the partial pressure of PCl3 if the temperature is raised. Let's see, do I have this one explained? Save us some time. All right, so there's your delta G. It's spontaneous. It does go that way. So we're looking for the ratio of partial pressures, right? Is this balanced? 3 chlorines, 2. Yeah, it's balanced. What happens when the temperature increases? Well, it's not giving it to me. Maybe there's an explanation down here. Yeah, here we go. If the spontaneous, the delta S is negative because we're going from 2 to 1. Okay. Delta G equals delta H minus T delta S. And this is going to be negative. This is going to be a negative value because it's more ordered. 1 versus 2. Okay. Delta G is negative. Okay. If this is negative, this term here would be positive. Right? So, and delta H, in order for this to be negative, this cannot be positive. If this is positive, then that can't work. So this has to be negative. It must be exothermic. Okay. So as the temperature is raised, what happens to the balance in this equilibrium? If we increase the temperature, that means this positive gets larger. And the reaction becomes less favorable. Can you say that again? We know this is negative because it's spontaneous. We know this is positive because it's 1 here and 2 here, right? Excuse me. This is positive because that's negative, more ordered. And with a negative sign, that's positive. And this has to be negative, otherwise that can't be negative. Okay, that's our starting position. Now, if we increase the temperature, what happens to the overall equation? Well, if we increase the temperature, that means this positive is getting bigger, which means as this gets bigger, it becomes less and less spontaneous until at some point that temperature gets so high that this shifts to a positive and now it's not spontaneous anymore. So on the way to non-spontaneous, we go through a series where the product is less favorable to be produced. So its partial pressure goes PCl5. Its partial pressure decreases as temperature increases. Okay? So as the temperature increases, this decreases, that increases, and the ratio then decreases. If you ratio that one against that one, you're seeing a steady decrease. PCl5 partial pressure to partial pressure of PCl3 is decreasing. With temperature. Okay. All right. So we threw in a little shot to get that one done. Okay. I'll leave that one up there, just in case. All right. Up to this point, we've been talking about standard conditions with a little zero next to it. But what we really want to know is, what is the delta G under actual conditions? Right? Delta G 0 is listed in the literature. You can look that up. But your conditions might not be standard. So we need a way to convert into a delta G that actually tells us whether the reaction under our conditions will be spontaneous or not. And these are two different equations, right? We're going to add those to this group, right? So the delta G, actual delta G, relative to the delta G standard conditions, we have to add RT log partial pressure, right? And this partial pressure would be for the entire reaction, right? So if you have 2 or 3 gases in there, you add them all together. The other possibility is if we have solutions and gases, we can calculate the Q. Delta G0 plus RT log Q. And this R has to be the one with the energy term in it. So remember that if we're at equilibrium, the reaction is not going anywhere. And that means this value is going to be 0. That value will still be its value because it's under standard conditions. But under our conditions, if it's at equilibrium, that one is 0. So if we're at equilibrium, you can equate either one of these to 0. Okay. And of course, if this is 0 at equilibrium, what does that become? K. That's the equilibrium constant. This is only a non-equilibrium, but at equilibrium, that's 0 and that's K. So under those conditions, if you know the K and the temperature, you can calculate delta G0. Or if you know delta G0 and your temperature, you can calculate K. Okay. So let's see, why did I stick this one in here? Delta G for a chemical reaction. A system can achieve the lowest possible free energy by going to equilibrium, not by going to completion. Okay. So the first one is supposedly the representation of a phase change. You're going from one phase A to another phase B, right? And it just keeps going until it's done. But for a chemical reaction, you can meet in the middle. Right? You can have an equilibrium where you have some product and some reactants. And that's what the C position is. It doesn't go to completion. It would only go to completion if your reaction could be fit into the left-hand model. And some reactions are very close to that one. They have such a small lip on the end, it might as well not be there. All right, so this is what I was talking about with equilibrium. If we set, say, this one equal to 0, at equilibrium, delta G is 0. It's not going forward or backwards. So now we have delta G0 plus RT, and this happens at equilibrium. So now we can say delta G0 is equal to negative RT log K. And I just took this over here on that side, change the sign, and then flip the equation. So we put this delta G0 on that side. Okay. So this is looking at, I don't even know if I need to. I think this particular slide, I should have pulled this one. I think it's kind of confusing. I'll try, but I don't know if I'm going to succeed. So how does the free energy change to reach equilibrium? Well, it says that if you're coming in as the fraction of A, if you go from A to B, that's the reaction. We're going from A gas to B gas. And we can go backwards also. The free energy of each gas is in these two equations. The free energy of, there it is. The free energy of A would be expressed this way, right, with its partial pressure. And the free energy of B would be this one with its partial pressure. And then the total free energy is the summation of the two. And the fraction of A is on this one. So that means if the fraction of A is 0.5, what's the fraction of B? 0.5. Right. So if we're right here, fraction of A, we're also 0.5 of B. If we're here at 0.75, then we're 0.25 B. Okay. So we're coming in from the other side, or we're coming in from this side, and we find out that at some point in here, based upon that previous slide where we had that final dip at the end, this is where you reach equilibrium at this fraction. And you also have the relationship of delta G for A and delta G for B. Delta G total equals delta G for A plus delta G for B. And as B, if we start off with A, then as B appears, it wants to go backwards. So in the beginning, it's all this one right here, right? At the very beginning of a reaction, it's all that one. But as you form B, then we start adding in this term. So what we're saying is, as long as the delta G for B is less than A, the reaction will proceed to the right. But once they're equal, once delta G and delta B are equal, then the delta G total is 0. So at equilibrium, that one has to be 0. And the delta G for A plus the delta G for B must be 0. All right, so as they approach, one is spontaneous and the other one, well, they're both spontaneous in the beginning, but once they reach equilibrium, then they must be equal and opposite in order to reach equilibrium. I don't know if that made a whole lot of sense. Let's go back to something a little bit more useful, like this one right here. Here we go. So we've looked at equilibrium constants before, and we find that for K equal 1, what would the log of 1 be? Right, this is base E. So E to the 0 is 1. Right, so the log of 1 would be 0. Right? If K is 1, if K equals 1, then that term is 0. That means the whole thing is equal to 0. So if K equals 1, then delta G is delta G0 is 0. And it's not spontaneous at all. I mean, it's just sits there. But if K is greater than 1, right, then we get a positive value here. That makes this negative, and this is greater than 1. That makes this one negative. Right, so now it's spontaneous. If K is less than 1, then we have the opposite effect. Less than 1 makes this negative, which makes that positive, makes this positive. So that's the generalized view of K related to delta G. So I think we're getting close to the end. Yep. All right. And I've gone over 40 minutes already. So back to Josiah Gibbs' original objective. How much of the work is useful? Delta G, Gibbs free energy, means that it's equal to the maximum amount of work that can be performed by any process. Right, so that's what the delta G is equal to, maximum work. Right. But we know that there are still losses. Up to this point, we've taken delta H and we've subtracted out the effect of entropy, right, to get our maximum work. But still, the actual work is going to be less than that. This is a theoretical value. The only time that this is operative is under ideal conditions of reversibility. In other words, the process can easily go backwards or forwards. And that only happens on the infinitesimal scale. And there we have to talk calculus to do that. So under real situations, the actual work is always less than the maximum. Okay. Let's see. All right, here we go. And if we set this one equal to this one, right, that would have to be delta G0 would be delta H0 minus T delta S0. They all have to be standard conditions in order for this equation to work. Then if we divide by RT, divide the whole thing through by RT, we get the next equation. Did I skip a step? Okay. If we're going to take this part here, now that we've equated these two, divide by RT, right? So now we have log K on this side, and we've divided everything through by RT. So that's delta H over RT minus delta S. And T's cancel, so we have R. Correct? Well, where we're going with this is straight line. So we're going to take this term right here and factor out the T. 1 over T. Right there. Okay? So now what do we have? We have Y equals mx plus b. So if we run an experiment and we plot 1 over the temperature as x, 1 over temperature in K, against log, not temperature K, but log KEQ, log KEQ. Plot those, then we get a straight line. Let's see. Oh, my mistake. That's positive. This is negative. Excuse me. Right? Because I divided by a negative RT. Negative RT over here, and then negative over here makes that positive. Okay. So we're going to get a negative slope, straight line. And the slope of that line is a negative delta H0 over R. That's the slope of the line. And the intercept of the line up here is equal to delta S0 over R. So if we run an experiment with at least 2 data points where we calculate K at different temperatures, and then plot the inverse of the temperature versus the natural log of K, we can get both the standard enthalpy from the reaction and the standard entropy from that data. And there's some real data. Oops, it's K to the -4. All right. All right. Oh, this is the last slide. All right. Achieving the maximum work available from a spontaneous process can occur only in a hypothetical pathway. Any real pathway wastes energy. That's bottom line. All real processes are irreversible. In other words, they go one way and they don't come back without some intervention. All right, okay. All right, this is kind of humorous. The first law can also be stated. Remember, the first law is the change in energy for the universe is equal to 0. Okay. That means you can't win. You can only break even, right? You can't get more energy than you put in. But the second law is a fly in the ointment. You can't even break even, right? Because you're losing some to entropy. Right. Second law says any transfer of energy will result in a waste of energy unless a temperature of absolute 0 can be achieved. That means never. And then the third one is you can't get out of the game, right? You cannot achieve absolute 0, period. So the bottom line is every time you use energy, you degrade its usefulness from that point on. There was you ever watched the series Stargate Atlantis? No. They've got this power source. The team from Earth goes to Atlantis in another galaxy, in the Pegasus galaxy, and they try to figure out what the ancients were doing with all this technology. And they found that the best energy source, which is in limited supply, is called a 0-point module. It's this big crystalline thing. It's got pretty colors and things. You put it in the device, and it powers up the whole city. In fact, it'll power a star drive. The city can take off a little faster than light. It's called a 0-point module because it takes advantage of entropy. It creates a vacuum space in subspace inside the crystal and taps that for energy production. So that's just an example of entertainment trying to make use of real science. We don't have access to that yet. We're still fossil fuels, maybe a little nuclear. Okay, we're done. I'm pretty sure we're done. Yeah.